So here is a sum gate. If you recall, the sum gate is this ternary gate right here. It's the fundamental gate of a ternary ALU, as it's the gate that allows us to get the addition of two trits. And it's quite a complicated gate compared to the simpler ones I described in the first article on the topic. So to create this sum gate, here is the diagram I have on my website. So this is actually the diagram for a n sum gate, and it uses the basic gates. Here is a n cons gate. It's negated because there is this circle. This is a any gate, and a n any gate. So in transistors, as I explained in one of the articles, the n cons and n any are cheaper to create. They actually require just two transistor CMOS pairs, so two chips. And to get the any or the cons gate, we have to actually negate the output with a NOT gate, which is a single chip, a single CMOS pair. So here, this whole tower of chips interconnected with the spaghetti of wires is a sum gate. So starting from the bottom, we have a n cons gate, and an nanny gate, and a NOT gate. So those three PCBs correspond to those two gates right here: the n cons gate, the n any gate, and the negated output to gate n any gate. Then we have another n any gate and a NOT gate. This corresponds to this one right here. And finally, another n any and NOT gate corresponding to the final one. This diagram is for a n sum game. This one is for a sum gate. So I'm gonna show you how it works. So this is my power supply unit. This is a transformer. It's a symmetrical transformer. So it's 12 volt, 12 volt. It's actually 24 volts across the two blue wires, but the black wire is the center tap, so we get 12 volts and 12 volts across the two pairs. And this is a classic power supply unit, dual rail, positive, negative, and it's created with basic linear regulators. So that's why I had to put heat sinks here. It's actually quite warm. And as you can see, the power supply here is set to a slight positive bias. I explained in one of the articles that the CMOS gates I used have a slight negative bias. So this is to compensate this. This is another power supply unit, the same, but I'm just not going to use it for this circuit. It's just for some tests. So the output of the dual rail power supply goes into this splitter. So one is to power the gates, and one is to power those couple of switches. So I'm going to show you how it actually works. I don't have an LED to visualize the output, so we're going to do this with the multimeter. So here is the input and output matrix. So as we can see, 0, 0 is 0. So that's what we observe right now. Plus and 0 equals plus. Plus and plus equals minus. Plus and 0 and plus equals plus. Plus and minus equals minus. Minus and minus equals plus. Minus and 0 equals minus. Minus and plus equals 0, and the opposite here. So this works perfectly, as you can see. So this is the basic component for the ALU. I'm gonna have to create another PCB to get this to a more manageable size. As you can see, this was my previous attempt at a sum gate. This is the symbol for a n sum gate, actually. but it didn't work. So after, well, I described this in one of the articles, but I had to add these small Zener diodes to the output, as well as a large, this is a 100k resistor to ground. So this creates a voltage shifter that creates a stable 0 volt output, a 0 volt state, and this is critical. I think that's what made this PCB not work properly. So I'm very excited to actually work on this project because I'm close to the end. Once I get a working some PCB, we're gonna be able to create a half adder, and then a full adder, and then eventually an ALU. So stay tuned to see more about this project. I hope to complete it in the next few weeks. So yeah, stay tuned.